Professor Bialis here. In this video, we are going to be talking about section 12.2, which covers inverse functions. But before we talk about inverse, there's something else we need to briefly introduce, which is called a one-to-one function. But before that, let's review just the basic definitions involved with functions. So first of all, we need to define that word relation. Now again, I like to keep it very, very simple. A relation is simply a set of ordered pairs. Now, those ordered pairs we are going to be thinking of as inputs and outputs. Okay, and those inputs and outputs typically are thought of as x and y coordinates. Okay, so function then. A function is first and foremost a relation. So it's a set of ordered pairs in which every input has one unique output. Okay, so for instance, let's say we have 5, 3, 6, 2, 7, 5, 8, 2. That's a function. Okay. If we had like a 5, 3, and then 5, 9, that would be wrong. Okay, that would not be a function because that input of 5 would have two different outputs. Here, 5 is only giving an output of 3, 6 only a 2, 7 only a 5, 8 only a 2. Okay, that is a function. Now, a step further from that, or to that, would be a one-to-one function. Okay, a one-to-one function first and foremost is a function, which is a relation. Okay, so this is a very specific relation. It's categorized as a function and a specific type of function. So, a one-to-one function is a function in which every output comes from one unique input. Okay, so up here with just regular functions, no input can be repeated with a different output. Now, same thing goes for the outputs. Okay, so like this function up here is perfectly fine, but it's not one-to-one because a 6 makes a 2 and an 8 makes a 2. That would not be one-to-one. Okay, we want to be able to say where a number came from. If I get a 2, it could have come from the 6, it could have come from the 8. Okay, if I got a 3, I know that it came from a 5. So a one-to-one function would be something like this. Let's say we have 11, 7, 8, 3, 4, 9, and let's say 3, 5. That would be a one-to-one function. Now you might be thinking, well, wait a minute, there's a 3 that got repeated, but it's an output once and an input once. That's okay. I just can't have a 3 be an output for two different numbers, or 3 be an input with two different outputs. I can't have that. Okay? So that's the difference between just a general relation, which is just any combination of ordered pairs, a function, and then more specifically a one-to-one function. Okay? Now, when we talked about functions in the past, we talked about how to identify if a graph was a function or not. Okay? Listing of ordered pairs, we could just look for that repetition in the x's, repetition in the y's. But how about a graph? Are these, I'm going to abbreviate one-to-one functions. And let's say we have something like that. Okay. Now, if you remember when we talked about just regular functions, we had what was called the vertical line test. Vertical line test states that if you can draw a vertical line, just one, a single vertical line that hits the graph more than once, it's not a function. Okay? So in this case, this passes the vertical line test because any vertical line I draw will only hit the graph at one point. Okay? Now how about one-to-one functions? One-to-one functions bring in the idea of a horizontal line test. Okay? This looked for repetition in the x's, which we were avoiding with functions. This looks for repetition in the y's, which we are avoiding in one-to-one functions. So if I draw a horizontal line that hits it more than once, no, it is not a function, or not a one-to-one function. Okay? Because, for instance, this could be 3, 4, and then this would be, let's say, -3, 4. Two different inputs have the same output. That is not one-to-one. Okay, how about this? How about something like that? Is that one-to-one? Well, we draw this. Yes, it is one-to-one. Let's do one more. How about this? Is that one-to-one? Now, if we do the horizontal line test, that's perfectly fine. Okay, it's only hitting it one time every time I draw a horizontal line. But it has to be not just one-to-one, it has to be a one-to-one function. Is that a function to begin with? No. This fails the vertical line test. So honestly, we shouldn't even gotten to the horizontal line test until we pass that vertical line test. Okay, so don't get so caught up in that one-to-one. It has to be a function to begin with. Okay, so does it pass the vertical line test? Yes. Then I do that horizontal line test to see if that function is also one-to-one. So in this case, this is not one-to-one. It's not even a function. Okay? Okay, now, the reason we talk about one-to-one functions is because now we're going to talk about inverse functions. Okay, so let's talk about this. Oops. Okay, inverse functions could be lists of ordered pairs, could be graphs, could be equation type functions. Okay, any way you look at it, any type of function you are encountering, to find the inverse, you simply switch the input and the output. Nothing more than that. So inverse functions. To find the inverse, switch the input and the output. That's all there is to it. Okay? What an inverse function does is if, let's say, a function turns a 5 into a 3, the inverse function will take that 3 and turn it back to a 5. If the function changes a 6 into a 2, the inverse, so a function changing 6 to 2, an inverse function will change that 2 back to a 6. Okay, so it basically undoes what the original function had done in the first place. So when we notate this, this is what it's going to look like. If this is f of x, let's just call this a function f. Inverse is going to be notated like so. That would be the inverse of a function with that -1 exponent. So if this is my original function, I am then going to write the inverse as 3, 5, 2, 6, 5, 7, 2, 8. And there we go. That's as simple as that. Now, some of you may already be noticing something. Why did I even talk about one-to-one functions? Because if that function is not one-to-one, and I take the inverse of it, what do I not have anymore? I am no longer a function. Okay? So that is an important aspect of inverse functions. They need to be one-to-one in the first place for the inverse to also be a function. Okay, that doesn't mean I can't take the inverse. It's just not going to be a function after I do that. Now, if I took a one-to-one function, and then I took the inverse of that one-to-one function, then what am I left with? 711, 38, 94, 53. Now I still have a function. Okay? There's no repetition in the x's here, no repetition in the x's here. The original function was a function, and its inverse will also be a function. Okay, so that's why it's important that we have that idea of one-to-one down, because we're typically, if we're going to look to being able to take an inverse and then get a function, we need that one-to-one to be established first. Okay? Now, another thing I want to point out about this. When we talked about domain and range in previous chapters, okay, we always calculated the domain. Okay? We never really looked at range unless it was given to us on a graph. Now we can get a range algebraically as well. Now, how is that the case? How is that possible? Because look at what happens here. If I look at a regular function that I have here, my domain, set of all x values, was 5, 6, 7, 8. The range was 3, 2, 5, and then I already had the 2. 3, 2, 5. Okay, if I look at the inverse, what do I have? Domain is 3, 2, 5. And the range is 5, 6, 7, 8. Do you notice anything about that? We basically flip-flopped the domain and range. Okay, so if we have algebraic methods of finding domains, if we can then get an inverse, we can find the domain of the inverse, which then becomes the range, and so forth. Okay, so there's a lot of implications to this that are very useful in the long haul. So let's go into the algebraic portion of this inverse discussion. Let's say I give you f of x equals 3x minus 2, and I say find that. That's the inverse of f. So to find the inverse, what did I say before? You switch the input and the output. What represents the input? X. What represents the output? F of x, which remember, f of x is simply a fancy way of writing y. So the first thing I would do here is reintroduce the y. Okay, so steps for this. Step 1, reintroduce the y. The next thing is when we actually take the inverse. Switch the x and y. Okay, what do I mean by that? Literally, where you see a y, write an x. Where you see an x, write a y. That's all. That's all there is to it. Now technically, there's your inverse. But that's what we call the implicit form of the inverse. It's implied there. We want to be able to get the explicit form. Now what I mean by that is, we need to be able to write it with this notation. So we need to get y alone again. So step 3 is solve for y. And there's going to be your inverse. Okay? So we've got something like this. I'm going to add a 2. I'm going to put that 3y first. And then I divide by 3. There's your y. Watch. I switch the notation out. And there's my inverse. Nothing more to it than that. Okay? So all it is write x in place of y in place of x, solve for that y, there's your inverse. Okay? Let's look at another one. Let's say we have f of x equals 5 over x plus 2. Okay? So let's find the inverse by first reintroducing the y and then switching the x and y. Okay? Now we just need to solve for y. So I'm going to clear that fraction to get xy plus 2x equals 5. And then I get that y by itself. So I would subtract the 2x. You could write 5 minus 2x if you'd like. And then divide everything by x. And there's my inverse. Just for good measure, let's use that inverse notation. There's my inverse function. Okay? Now, here's something that I want to be very clear on. So let's see how this is going to play out. Let's go back to that idea of domain and range. In the past, all I could do is look at this function and say the domain is the set of all x such that x is any real number, but x is not equal to -2. Now, how did I get that? Just to make sure we're all on the same page. I would set this denominator equal to 0, subtract the 2, and that would be my restriction. That's all I could do. That's my domain. Same thing here. I would set that denominator equal to 0 and say the domain set of all x such that x is any real number, but x is not equal to 0. Okay? Now remember what we were talking about here. The domain of the function is the range of the inverse. The domain of the inverse is the range of the function. So now, given the idea of inverse, we have an algebraic method for finding the range. We didn't have that before. We just found the domain and that's all we could do. But now, if the domain of the inverse is this, then the range of the original one is the same thing. We have to tweak it a little bit. Watch what I mean. I'm talking about y values such that y is any real number, but y is not equal to 0. And the same thing down here, the range here, all the y's such that y is any real number, but y is not equal to -2. Okay? So again, algebraically, all we're doing is a little bit of manipulation, but then that domain and range, that is huge, because otherwise we would not be able to find any range values until we went through the process of graphing. Okay? Now, the other thing I want to point out is, why did we talk about composition of functions in the previous section and now inverses? It just seems like two random things put together. Because if we ever wanted to check if these two were actually inverses of each other, we can use composition. Let me show you how it works on this example here. Let's say they ever ask you to verify that two functions are inverses, or they say, here, here's two functions, verify their inverses. Okay? What should always be true is that a function composed with its inverse should always equal just a plain old x. However, this is not commutative, so we have to make sure it goes both ways. So we have to find both of those compositions. If both of these compositions equal x, then we can verify that they are in fact inverses of each other. Okay? Because this function changes it to some output, this should change it back to how we started. Again, inverse functions undo each other. So by equaling x, we're going back to that original input. Okay, so you plug it into a function, it changes it, then the second function changes it back. But we need to make sure it goes in both ways. Let's just do one of these just so you can see how it plays out. So I'm going to start with f, which is 5 over x plus 2. And then I plug in the inverse that I found, which is negative 2x plus 5 over x. Okay, so we're left with a complex fraction. Remember, with complex fractions, I can just multiply all three components by the LCD of x. So that gives me 5x over negative 2x plus 5 plus 2x. These cancel out, so I have 5x over 5, and all of that simplifies to just a regular x. Okay, if I went the other way, f inverse, that's a negative 2x plus 5 over x. Then in there, let me use a different color here, I would plug in that original, which is 5 over x plus 2, 5 over x plus 2. Okay, the first thing I would probably do with this is I would multiply these together to get a negative 10 over x plus 2 plus 5 over 5 over x plus 2. Okay, again, complex fraction. I'm going to clear it, multiplying all of those components. Canceling to get a negative 10, distributing to get 5x plus 10, and then I get a 5. These cancel, so I get 5x over 5, and I get an x. Again, what I just did here was I checked, I verified that these two were inverses of each other. Okay? You don't have to do that every time. If you want to check it, this is how you would do it. Or if they ask you, verify that these two functions are inverses, you do one composition and then the other composition. And they should both come out as x. If they don't, they're not inverses of each other. Either you made a mistake when you're doing it, or you made a mistake when you were finding that. Okay? Or you might say, the two you gave me aren't inverses. It just doesn't work. Okay? Now, the only other thing that they really talk about in this section is the idea of graphing inverse functions. Now, honestly, all that comes down to, again, is switching x and y. What I like to do is if I have a graph and then I, pick a few ordered pairs off of that graph, I simply take those ordered pairs and I flip the coordinates, plot the new ones, and then I go from there. There's really nothing more to it than that. Okay? What I want you to really focus on is this stuff right here, when we're finding the inverse. And then also this, because that's where the algebra really is going to be found. Okay? Let's do one more example like this, and then we'll call it quits for this section. So let's say I want you to find the inverse function, and I give you f of x equals x plus 3 over x minus 7. Okay? If you want, you can pause the video here and try to work that out on your own, get as far as you can. I'll be here waiting for you. Okay? So what we're going to do is we're going to reintroduce the y. Then I'm going to clear that fraction. Okay, now here what I would do, I'm sorry, don't clear the fraction yet. We needed to do the inverse first. So this was x minus 7. Now, to do the inverse, my apologies, I'm going to make that change. Now I clear the fraction. Okay, so again, I apologize if that threw you off. I reintroduce the y, then I make the change. Now I start working algebraically. So I'm going to clear that fraction. Now here, a lot of people want to leave that the way it is. I would distribute it because there's a lot of different terms you're going to have to switch around. Lay it all out. So I have xy minus 7x equals y plus 3. Okay, now remember, here you are trying to solve for y. You want y to be by itself. There's two terms with a y in it. So the next thing you need to accomplish is get all the y terms together. You can't isolate the y when there's two of them. But you can get all the y terms together and then all the non-y terms on the other side. So I'm going to subtract y and then add a 7x. So I've got xy minus y equals 7x plus 3. Okay? What I can then do, why I wanted all those y terms together, I can simply take that out as a GCF. Now I only have one y. And I get x minus 1. And then I can divide by x minus 1. And then, just for good measure, there's your inverse function. Okay? And just like before, if you want, you could take this, compose it with this, make sure you get an x, and then take this, compose it with that, make sure you get an x. Let me just show you one of those ways. Okay? Again, just so that we can see these more complicated scenarios laid out. Okay, so if I go with f composed with f inverse of x, I start with my original function, which is x plus 3 over x minus 7. And then in there, I plug in that inverse I found, which is 7x plus 3 over x minus 1. Okay, complex fraction. I want to clear that. So I am going to multiply each of these terms by that x minus 1 LCD. This will cancel. So I get 7x plus 3 plus 3x minus 3 over 7x plus 3 minus 7x plus 7 after I distributed that negative 7. Okay, this should be a quantity here and here. Okay, now let's clean that up. These go away, so do these. So I get 10x over 10, which is just an x. Now remember, that doesn't verify it yet. I have to do the composition on the other side. I will leave that up to you. Okay? If you have any questions on it, again, please feel free to reach out. But to really verify this, I better make sure that this also just equals an x. It's going to be very similar to this right here. Okay? So, again, we're talking about that whole idea of a one-to-one function. No repetition in x's, no repetition in the y's. Then we talk about inverses, which, simply stated, you're switching the x's and y's, switching the inputs and outputs. What that allows us to do is open up that idea of domain and range. It allows us to find different versions of that so that we can undo things, okay? Because again, inverses undo each other, and so on. So again, switch the x and y's. Just keep that in your head and be careful with your algebra, and you'll do great. Okay, so as always, work hard. Let me know if you have any questions. I'll see you next time.